In this unit, we're going to introduce the concept of states of matter, what it takes for you to change between states of matter, and the energy that's associated with changing states of matter. The first half will mostly be focused on the states of matter, and as you can see here, and also the way that they change. And then later on, we'll talk about the energies that's involved. So you can see here that we're mostly going to end up looking at the kinetic molecular theory to start, and then also the particle behaviors of solids, liquids, and gases. Eventually, we'll get into the structure of water, the changing of states of matter, and the energies associated with it. But definitely, these first two are ones that pretty much imply or apply throughout the entire unit. We'll use these pretty heavily in this first set of slides. So let's introduce the kinetic molecular theory of matter. Before I move on, the word kinetic, that refers to motion, so kinetic, right? Molecular referring to individual molecules, and then the word theory, of course, is overarching pattern of behaviors that we can observe and explains why things occur the way they do. We're actually going to kind of sort of adjust a little bit of this. The word molecular, that again refers to molecules, and those are, things that are individual groupings of stuff, of different atoms together. But that's kind of a very, very broad definition. The term molecular really just applies to any particle, any tiny, tiny particle. And that refers again also to individual atoms themselves of different sizes and shapes. So the word molecular doesn't refer to just molecules. It refers to any tiny particle. So essentially this is about the theory of how molecules move. The definition behind this is the theory that behaviors of gases, liquids, and other solids, let's try that again, can be explained by the behavior of its particles. So the particles on the tiny, tiny, minuscule, almost invisible scale, those behaviors can show us how things on the visible scale work. So this accounts for movements, appearance, and so on and so forth. Any state of matter is dependent on two major components typically viewed as conflicting forces, and they are particle motion, which relates to kinetic energy, which we'll talk about a little bit later, and also, little throwback here, intermolecular forces, right? So these attractive forces that exist between different particles. Once again, that word molecule shows up again, or molecular, that form. That's not really specifically talking about just molecules alone, but pretty much any particle, any tiny particle that matter is comprised of. So to kind of put context in this, remember that when you talk about gas particles, the two components, kinetic energy and intermolecular forces, which one of these two plays a larger role in its state of matter? So if you think about gases, gases are freely moving about, they're zipping around. So then its kinetic energy actually ends up playing a larger role than the intermolecular forces, the sticky forces that keep the particles from moving freely. On the other hand, what about solids? Well, solids, again, as you can imagine, you see here at least, this is a little diagram of what we see on the particle scale. The solids, right, their particles are all locked into place and they're kind of vibrating in that place. And so what we can imagine here is that actually, the intermolecular forces would play a bigger role. Right? So those attractive forces play a bigger role than the kinetic motions or movements. So that's why a solid is a solid, because its particles are locked into place. Kinetic energy is one that we can just kind of say here and there, but there's actually a mathematical relationship that helps us know this. It's the energy associated with movement. And when it comes to movement, there are two main factors. You have velocity and you have mass. Well, mass I think is pretty understandable. Right? The more particles and the more mass there is, the bigger it is, the more mass it has. And then the word velocity really refers to the speed of an object. For those of you who've taken physics, they're not exactly the same thing, but they're close enough. So velocity, again, is the speed, mass is the size. And so we're going to look at, again, these motions of particles, right? So we're talking a lot about these particles. And so when we look at this, we want to think about how big the particles are and how fast these atoms or molecules are moving. You see here, you got the formula kinetic energy, Ke, is equal to 1/2 times mass times whatever velocity squared. So a couple of illustrations here, you see on the right side anyway, you have a small particle, you have a big particle, and again they're moving at different speeds, so this one's going to have much greater kinetic energy than this one right here. Even if they have the same size, so these two guys are about the same size, but this one obviously shows motion moving a lot faster than the one right here on the left. This guy on the right is going to potentially have, or effectively going to have, higher kinetic energy. That value of V is going to be much greater when you're running than when you're walking, right? V meaning velocity, which is the same thing as your speed. Couple of text illustrations. A particle moving slowly has less kinetic energy than the same particle moving quickly. So if I know that my mass is the same, all right, so a single particle, the mass isn't any bigger or smaller than the other because it's the same particle. The value of mass times velocity squared is going to be smaller for a slower moving particle than for a faster moving particle. On the other hand, you have a smaller particle will have less kinetic energy than a larger particle moving at the same velocity. So again, if two things have the same speed, where this term more or less is the same, and the only thing that changes is the mass, the smaller the mass, the smaller the kinetic energy. One more thing also to recognize, generally speaking, the higher the temperature of your substance, the higher the kinetic energy. And that's something we'll discuss later on in more depth. But the idea is that the hotter something is, the more kinetic energy, the more motion those particles have. Intermolecular forces, this one again just a brief review. This is just the temporary attractions that form between particles of a substance as they kind of bounce around, as they float around. This is what sort of happens that allows them to be temporarily attracted. There are three main types: Lindner dispersion forces, dipole-dipole interactions, hydrogen bonding. We're not going to spend a ton of time going over each of those, but just know that, of course, those three together comprise the possible intermolecular forces that exist. And as you can imagine, the higher the intermolecular forces, the stronger the attraction. So these, again, are worthwhile relationships to understand and memorize. So, for example, water has really high intermolecular forces. Therefore, it has a higher boiling point, and therefore, you need a higher kinetic energy to disrupt those intermolecular forces. On the other hand, helium has very low intermolecular forces, right? You might not remember why necessarily, but that's something that you can assess and figure out. So that means the lower intermolecular forces mean that there's a lower boiling point, and therefore lower kinetic energy needed to disrupt the IMFs that would keep them from moving freely. So any substance has the same intermolecular forces present. For example, water, no matter if it's an ice, whether it's water form or vapor form or liquid form, water is always going to have some hydrogen bonding present because that's just how it is. That amount doesn't change. What does change between those three, right? Ice, solid, liquid, and gas, those are going to be dependent on the temperature and the way that kinetic energy is in those particles. Now, specifically about gases. So we're going to basically take kinetic molecular theory, that theory that particles, again, can explain why things behave the way they do on a larger scale. We're going to apply that to gases. So gases, one quick definition that you might remember, a state of matter that does not have a definite shape or a definite volume. So it'll take the shape of its container, whatever it might be, but also doesn't have a definite volume because it can expand and contract depending on the size of your container or whatever it's in. So the kinetic molecular theory describes the behavior of an ideal gas, which is basically a gas whose particles have the following 5 properties. Now, really quickly, the word ideal, right? That means something that it works perfectly and according to the rules and does everything it's supposed to. That's an ideal gas. And so this is very much a theoretical construct, right? There's making some assumptions. And so the kinetic molecular theory, right, as a particle descriptor, describes these 5 things. So every gas, the reason why gases behave the way they do is because, one, gases consist of a very large number of tiny particles that are very far apart. So you can see right here on the right side, this little illustration, all those little tiny particles, right? They're kind of zipping around. But notice how there's a ton of space between them. Now, in fact, this is actually not even really to scale. If you take a normal size sample of gas, like say, for example, the air that's around you in your room or something, or in the classroom, that's going to end up being, lots and lots of space, so much empty space. So this is, again, not even to scale. These particles would be so much smaller if this really truly were to represent scale. That space between these is very, very large. Number 2, IMS between the gas particles are negligible. So there are some attractions that might occur as these particles get close to each other. But because, again, we're assuming that the intermolecular forces play such a small role, they're considered negligible or, effectively non-existent right now. Part number 3, the gas particles are in constant, continuous rate of motion and thus possess some kinetic energy, right? Thus, therefore, have some motion involved, therefore, some energy associated with that motion. And number 4, collisions of gas particles and walls or particles in themselves, right? So between whatever it bounces off of or whatnot, these are considered elastic collisions. Now, the word elastic probably, conjures up images of, probably stretchy things, and that's kind of true in terms of what this means, but really what the collision means, these kinds of elastic collisions, it means that when the particles collide, no kinetic energy is lost. So they bounce off each other, kind of where nothing really holds them, keeps the energy from being transferred directly. There's no stickiness from the IMFs. So if you can imagine, right, if you're playing pool, for example, if you play billiards, those pool balls, right, when they bounce off each other, as they bounce around, they kind of slow down after a while because the felt there, like the felt that's running on, slows them down. But imagine if they could float around in space where there's no friction, they always bounce around. So that's essentially, if you imagine all of them bouncing around and never stopping, that's what they mean by having elastic collisions, right? No stickiness, nothing about those balls themselves makes them stick to each other. Number 5, the temperature of a gas represents the average kinetic energy of the particles of a gas. So all the individual particles floating around, like these right here, right? If you have them moving faster, that means they have greater kinetic energy, which means that your sample has more temperature, higher temperature. That's fairly intuitive. Let's go and connect what we have here with the kinetic molecular theory. So now these are the properties. We just described gases as a whole. There are specific properties that a gas does, and that we can again explain it based on those 5 parts of the kinetic molecular theory. So what we can see here, right, the visible behavior can be explained by the kinetic molecular theory, which explains this invisible particles. And these are summarized right here again. I went ahead and copied them from a previous page, obviously. You're welcome to do so and reference it from here. All right, the first one is expansion. So gases will expand to fill its container. Now, expansion is illustrated by this guy right here. You have these 2 large vessels, one of which has a lot of particles, one of which doesn't, and then you have this sort of stopper in between. And what happens here is that this gas, right, is all contained here. But the second you open this up, the second you open up the stopper, the gases in their constant random motion, right, because you have all this constant random motion, this kinetic energy or this kinetic motion will allow them to bounce around and eventually start to fill up this space over here. Right, this one's completely empty to start, and so when you have this open, it's going to fill in that empty space. It's constant random motion that'll fill it up. So that's the main part of how, again, expansion works. Now, don't get me wrong, right? The fact that there are a lot of very, very large number of particles with very much space between them, right? That's still true. It might not be necessarily to scale in this diagram, but that's still true. We're still assuming that the IMFs between gas particles are negligible and so on and so forth. But again, the main factor that explains this behavior would be something like 3. Fluidity, right? Fluidity is this idea that these particles all sort of flow past each other. And that again comes down to constant random motion. And also the fact that these particles, when they collide off each other, they don't get stuck to each other, right? There's no sort of extra sort of attachments they have or attractions that keeps them from flowing freely and moving about. So that's where part number 4 is probably most useful, right? Again, we're not saying that 1 through 3 and 5 are not used here. We're just saying that the most important of the 5 that helps explain this fluidity is part 4. Low density, right? Low density meaning that you have in this expression of mass over volume. The value of this right here, your density, is actually going to get smaller if mass goes down, right? Or if your volume goes up a bunch. Well, if you think about it, right, we have a container, a single container here, and you have a lot of particles in there, right, versus the same container with very few particles in here, which is going to have a lower density. It's going to be the one on the right because there's fewer particles in here, and we know that the particles are responsible for the mass that's present. So that means in the same volume, if you have a lower volume value of m, that's going to give you a smaller density. So having a low density, right, again, knowing that how gases behave, which one of these do you think is the most responsible for low density? Well, it ends up being part 1, right, because gases consist of a very large number of tiny particles that are very far apart. There's so much empty space between them that you actually end up having such a low density when it comes to gases. Here, there's a couple more properties, and I want you to go and take a look at them. See that, compressibility, for example, is the fact that you can take particles, or a gas anyway that's in a container, and then you can compress it into a smaller space. And then diffusion and effusion, we'll talk about in the next slide, but that's basically how well something can pass through an opening, or how well it mixes with other gases. So go ahead and try to connect these 2 with one of these 5, if not more, these kinetic molecular theory parts. To finish off, I'm going to talk about how air freshener works really quickly, at least how the gases work, in terms of diffusion and effusion. So let's start off with effusion, actually. This is about gas particles passing through a tiny opening. So let's say you push the little button on the air freshener, and stuff sprays out. Well, what is that stuff? That's actually air particles, right? That air particles are passing through a small opening. That's the act of effusion. And then diffusion is, say you spray that in the corner of a room, and then that room, because there's already air particles around, is going to allow these smelly particles to float throughout the room and mix around. So that's essentially diffusion. So effusion is about passing through a small opening. Diffusion is about spreading through a mixing of gases. And that more or less takes care of that. So you can think about when it comes to the previous slide where I asked you to identify which of the 5 parts is most relevant for diffusion and effusion. You kind of use that as a visual to help you explain how which one of these 5, if not more, would apply. All right, the very last thing here is deviations from ideal behavior. Of course, we described ideal behavior, meaning it feels perfect and worked according to the rules and the laws as it's supposed to. But of course, it doesn't quite do that. So just go and take a quick look at this and to memorize which factors keep it from being ideal. All right, that'll do it.